Are you confused or worried about whether AI can take over our jobs? You want to grow as a professional in machine learning, but you're afraid that your job will be snatched away by artificial intelligence and automation in the near future? There is hope. In this video, I will use a practical industrial business use case of machine learning to show why human beings will still be required even if AI and full automation takes over. Now, let's take Wi-Fi internet speed as a business problem. Everybody loves an internet connection with good speed. Let us say there is a coffee shop that offers its customers free Wi-Fi. If customers do not get a good Wi-Fi speed at the cafe, they may form a bad impression of the cafe. Are you wondering why the cafe owners should care? They should, because having a poor Wi-Fi at the cafe can hurt the cafe's business. Even though the cafe may only sell coffee and cakes, it can lose its customers to a competitor simply because that competitor offers better Wi-Fi. So there is business value for this cafe in monitoring Wi-Fi speed and managing it so that their customers are happy with the Wi-Fi speed and happy with their business. There are many ways to solve problems like this, and machine learning is one of the faster and more profitable ones today. Real world industry problems like this have many parts that have to be solved step by step, sometimes involving multiple projects and teams. Now, let's come back to the business problem of using machine learning to manage Wi-Fi speed. Like every machine learning project, we should begin with collecting data on Wi-Fi speed. One bonus with this one is that you can set up a learning project right in your home. Using a laptop, you can collect data about your home Wi-Fi speed. There are many websites which allow you to do so. Just Google speed test. Beware though, this kind of speed test may consume data, so if you're worried about your home internet bill, you're welcome to use the data I have collected for this tutorial instead. Link to download the data is in the description. Next, let's look at a job role for a machine learning professional. Your job may be to identify outliers in your Wi-Fi speed data. Outliers are values in your dataset that stand out from the rest of the data. We need to identify and, if necessary, remove outliers or anomalies from our dataset before the dataset can be used for other processes in machine learning. This activity is part of a process called data cleansing. For datasets like this, one of the methods that I generally use to detect outliers or anomalies is the Z-score method. Let's quickly walk through the Z-score method. I've collected 132 Wi-Fi speed test samples over a period of 5 days in my sample Wi-Fi speed dataset. You can download it from the link in the description. Now, if we look at the download speed data in megabits per second, at 6:17 p.m. on March 21st, the download speed was 17.04 megabits per second. At 6:22 p.m. that day, the download speed was 22.89 megabits per second. Let's scroll down to another sample. At 11:23 a.m. on March 22, the download speed was 27.32 Mbps. And so on and so forth. Given this data set, we need to identify the download speed values that are significantly different from the rest of the values here. These values may indicate outliers or anomalies depending on the situation. To use the Z-score method, our first step is to decide if our dataset fits the normal or Gaussian distribution. If the data fits the normal distribution, then we can use the mean and standard deviation of the data to calculate our z-score. Let's plot a histogram for our sample data set. Here is some Python code to plot our histogram. So first, all the necessary imports of Python libraries. We need matplotlib to plot our histograms and the distribution curve. And we need the pandas library to load our Wi-Fi download speed data. And we need the stats library to actually come up with the statistical calculations, including the Box-Cox Transform and the plot of the normal distribution. So the first step is to load the test data, the 132 samples of Wi-Fi download speed in megabits per second. I don't have a header in the file, so I'm indicating that I don't want to load and interpret the header. I want all rows to be treated as data. So just a peek into the data set that was loaded into a data frame. df is the variable that holds the data frame. And let's run the code this far to load the data. So we can see that the data frame has loaded successfully. Now let's plot out the data, the Wi-Fi download speed data in Mbps, in megabits per second. So I'm going to plot a histogram. With the data frame df. Oops, there is a syntax error there. I was missing a comma. Okay, so here is the plot. We can see that there is a right tail to this plot. So obviously it's not an ideal Gaussian or a normal distribution. And it has two peaks as well, rather than one. At least that's how the sample data set is looking. In my opinion, our data does not look normally distributed. If this data is actually normally distributed, it might need a transformation to reveal its normality. We're going to try the Box-Cox transformation, which is a statistical method commonly used to reveal normality when the data looks skewed. With this method, we raise the distribution of our data to a power of lambda. This transforms our non-normal distribution into normal distribution. The lambda parameter for Box-Cox can be anywhere in the range -5 to +5. So let's say we find from our Box-Cox transformation that our lambda is equal to 3. Then we raise our distribution to the power of 3. That is y is raised to x cubed. There is an exception though, when lambda is 0, in which case we will transform our distribution y to log of x. The formula are showing on your screen. So let's now proceed to the Box-Cox transformation of our dataset. Here is some Python code to do so. We should be calculating the Box-Cox transform from our data frame. So the transform data will be held in a new variable, in a new data frame, df_trans. And we're going to calculate the lambda parameter, which determines the power to which the data needs to be raised in order to do the transform. So the stats.boxcox method will calculate the lambda and also give us the transform data set with that lambda. So let's go ahead and plot the transform data set and look at what was the best calculated lambda from our data set. Let's round our lambda to 4 places of decimal. There's a syntax error. It's missing a bracket here. Let's rerun. Okay, there we go. 0.3807 is the calculated best lambda. And let's take a peek at the data frame, the transformed data frame, the df underscore trans data frame, which is the output from the Box-Cox transform. Now let's go ahead and calculate the parameters of the normal distribution, mean and standard deviation from df underscore trans, because now our assumption is that with the Box-Cox transform, df underscore trans should exhibit normal distribution. So we're going to use the stats.norm.pdf function to generate the probability distribution function using the calculated mean and standard deviation as the parameters of that distribution. So what was the calculated mean? 6.6649, and the calculated standard deviation 2.529. So you can see that we're using the mean and standard deviation that we calculated with the norm.fit function. The stats.norm.fit function fits a normal curve on df underscore trans and gives us the parameters of that fitted normal curve. Those parameters are the mean and standard deviation. And then we supply the mean and standard deviation to the stats.norm.pdf function to generate the probability distribution curve corresponding to that normal distribution. And now our next step would be to superimpose that probability distribution curve on top of the transform data, the Box-Cox transform data, that is df underscore trans, which should give us an interpretation of how the fitted normal curve looks like on top of the transform data. So let's go ahead and come up with the plot. We can't see the probability distribution function being plotted somehow, but we do see that we have a plot of the Box-Cox transform data, the blue bars over here, which probably looks a little bit closer to a normal distribution in my opinion. Okay, we know where the issue is. We have to set density to true in order for the probability distribution function to be plotted correctly. The orange graph, which is superimposed on top of the blue bars representing the Box-Cox transform dataset, df underscore trans. Finally, we plot the transformed dataset df underscore trans and superimpose the fitted normal distribution curve. This gives us a picture of the approximate normal distribution we obtain after doing a Box-Cox transformation of our original Wi-Fi download speed data. If we are satisfied that the normal distribution is a reasonable estimate of the Box-Cox transformation of our original Wi-Fi download speed data, we can apply the mean and standard deviation values from this fitted normal distribution to calculate our z-score, which in turn should allow us to detect the outliers in that normal distribution, which is our goal anyway. Notice that I said if we are satisfied that the normal distribution is a reasonable estimate. This is a big if. And I say it is a big if because here is one example where human beings still have a better role to play over AI and machines. Through our research, we human beings have better knowledge of the physical processes that govern Wi Fi download speed. For example, the factors that cause variations in the speed, such as distance of your computer from the Wi Fi router, repeater, or hotspot, the number of people who are using Wi Fi in the same frequency band as your Wi Fi is on, and the hardware capability of your computer's network card, etc. We call this domain knowledge, the knowledge of the scientific and engineering principles that interact together to establish a whole range of Wi Fi speed values that are possible in a given situation. Many times we find ourselves needing to apply this domain knowledge in addition to pure statistical studies of our data to decide whether normal distribution, or for that matter, any other distribution, is appropriate for our data set or not. Only when we have made an informed decision about the normality of data can we apply normal distribution principles such as z-score to detect outliers or anomalies in our dataset. Your dataset doesn't have to fit a normal distribution. Several real-life data are not normally distributed. Time required to repair a system component malfunction can follow exponential distribution, and reliability analysis of performance of a machine over time can follow Weibull distribution. Distributions like this are revealed through research and observation of a great deal of historical data. Obviously, you would be hesitant to fit the normal or Gaussian distribution to a dataset if you knew that dataset came from a domain or physical process that lends itself better to, let's say, exponential distribution. Now, you might say that a tool like ChatGPT already possesses this domain knowledge about Wi Fi, and therefore ChatGPT might be equally capable to make such determination of normal distribution, thus making the role of a human being redundant. Well, you could be right that ChatGPT might be better and faster at making such a decision if it has existing information available to actually logically make that decision or reach a conclusion. Here, existing information could be scientific study on very large amounts of Wi-Fi's download speeds from various different Wi-Fi settings across the world, something that established that Wi-Fi download speed follows normal distribution. This kind of decision making by a tool like ChatGPT is called System 1 thinking. However, let's say that there is not enough information about normality of Wi-Fi download speed out there already. Let's just assume that. Then this kind of study might require a conscious, slow, effortful, and logical thinking, which is how our human brains work when solving more complicated problems. This is called System 2 thinking. So the point I'm trying to make is whenever there is opportunity for system 2 thinking in any problem, human beings are still going to be needed to use our conscious, deliberate thinking. Hopefully we human beings can open up more capacity and space for higher thinking and keep our jobs in system 2 thinking as we continue to offload automatic system 1 type work to AI and machines. This is my view anyway. Please let me know in your comments what you think. Do you feel like this would be the space, or this would be one of the spaces where human intelligence would continue to be needed, and therefore tech professionals would still be needed while we make quantum leaps to artificial intelligence and automation? Do you feel like the fear about jobs being taken away by AI can be countered with this kind of knowledge and by moving up the value chain of domain knowledge, to let us know. If you feel like this video helped you think about a problem that faces us in the tech community today, and if you felt that this video was of any value to you, please share this video with your friends and subscribe to our channel for more such content. Thank you.